So, I'm gonna stop making any album reviews or movie reviews or TV reviews until May. So yeah. Anyways, if you have clicked onto this video or tapped onto this video, congratulations, because in this video I'm going to spend a very large amount of time talking about everything that has been taught to me in physics class from 10th grade to 12th grade. 3 years, okay? 3 years of physics. And I'm also going to do the same thing for chemistry and biology as well in preparation for my ultimate exams that are the DSEs. And I don't know if there is such an exam system in the USA. I'm not familiar with the whole American education system thing, or British. Actually, I'm pretty sure that in the UK you need to take the A levels, I think, or something like that. And A levels is similar to DSEs in that you need to take a few subjects and you take the best 5 subjects or exams that you've done, and you sort of add them together in some ways, and it determines if you can go into university or not, and a good university or not. But I don't think there is such an exam in USA. I mean, there are the SATs, but what the hell do they mean? SATs is basically English and maths. That's it. But realistically, every class you take in high school / secondary school should also have an exam. So I have done this already before a couple months ago, but back then I was not that familiar with physics. Now I think I'm better. I'm still not an expert, but here we go. Physics, everything. All right. So starting off, so if you don't study in Hong Kong, you can also check out what kind of stuff we study here in Hong Kong. Anyways, first book, Heat and Gases. Heat is actually the easiest part in the entire syllabus. I am going over it once again, because why the hell not? So what you really need to pay attention to, of course, boiling point, melting point, everybody knows about that stuff. Easy stuff, primary / elementary school stuff, everybody knows that. Now we can quickly skip over to 1.2, thermometers. And there are several kinds of thermometers. We have the liquid and glass thermometer, we have the infrared thermometer, we have the rotary thermometer, we have the resistance thermometer, the thermistor thermometer, and the liquid crystal thermometer. And there are also 2 kinds of liquid and glass thermometers, one with mercury and one with alcohol. The mercury is better, but if you break it, you're dead. Alcohol is safer because mercury is poisonous. Alright. Up next, we have the one and only specific heat capacity. Energy equals to delta T mc. Delta T is the change in temperature, the rise in temperature basically, equals to M, mass, in the unit of kilograms, and C being the specific heat capacity. We also have the concept of internal energy, as you can see here. Now here's the thing, if you heat something up, like say a bowl of water, a pot of water, and you heat it up from 0 degrees when it is liquid to 99.9 degrees, the potential energy did not change at all, but the kinetic energy definitely changed. But say you heat ice, and after you heat up the ice turns to water and it rises from 0 degrees to 10 degrees. Then there is both rise in potential energy and kinetic energy. kinetic energy, and the rise in potential energy is the result of the changing of the state between the solid and the liquid. And we also have internal energy, which is basically all sorts of energies all combined, potential, kinetic, and also mass. It's related to mass as well. But of course, specific heat capacity is extremely important. And also, specific heat capacity is used to determine only the kinetic energy, but if you want to know the potential energy being supplied to the object to change its state, either from solid to liquid, you have the specific latent heat of fusion, and from liquid to gas, you have the specific latent heat of vaporization. So as you can see, we have the equations here. And we also have other types of, there we go, latent heat. Latent heat. Now, there are three ways that heat can transmit. We have conduction, convection, and radiation. Also evaporation, but it's not really. So for conduction, it's easy, molecules, they vibrate faster, and the whole thing becomes very fast and expanded. Conduction is easy. For convection, it happens in fluids. So the hot air, they rise. The hot fluids, they rise because they are less dense. But then the heat source is underneath. So the cold fluids also get heat up. So it just becomes a cycle, a convection current. We also have radiation, which also works in vacuum space. That is why we receive heat from the sun. There's also evaporation. All right. Yeah, not much else to talk about here. Again, conduction, convection, yada yada. We can quickly skip this over. It's pretty easy, really easy chapter. One thing to notice is that shiny and light-colored surfaces are poor absorbers and poor radiators of radiation, which means that if you don't want to feel super hot, but you live in a really hot place, just feel free to paint your house white. Then it'll be a little cooler. If you live in a really cold place, then just paint your house black. As you can see right here. But yeah, other than that, let's get this over with. Now, moving over to the second part of the book, gases. This is a little more complicated, but it starts off really easy with PV over T equals to PV over T, meaning that these things are constant. The pressure and volume of temperature of a gas is always constant, and they are not always constant, always proportional to one another. Why? Of course they're not constant. What? So pressure, Pascal, is basically Newton per meter square. And we have PV over T equals to PV over T. We have the Boyle's law, the Charles law. The Boyle's law being P is inversely proportional to V. So pressure is inversely proportional to volume. And then we have the pressure-temperature relationship, and then we have the Charles law, which is basically volume is directly proportional to temperature. In Kelvin, of course, if you want to calculate this. Now we have an even more complex formula right here, PV equals to nRT. P being the pressure in Pascal, V being meters cube, equals to N equals the number of moles of gas. So 1 mole of gas has 6.022 times 10 to the power of 23 number of molecules. R is 8.31 is the universal gas constant, and T is temperature in Kelvin. And we also have the one and only. Okay, so I don't know if this is a part of the syllabus or not, but a smoke particle moves along a zigzag path. just so you know. PV equals to 1 over 3 nmc squared, c squared being the average speed of each molecule. And this is directly related to the kinetic energy of the gas. And because it is the average speed. And okay, it gets super complicated here. I'm gonna have to show you guys this. Basically what we have here is a very important, very important equation, and that is the average kinetic energy of the gas equals to 3 RT over 2 NA, NA being Avogadro's number, 6.022 to the times 10 to the power 23. And the internal energy of a gas is 3 over 2 nRT. And I think other than that, we have pretty much covered the whole book. Yeah, I have my own notebook here as well, if you're wondering. But I don't know if you guys can understand anything from my notebook because it's a clustered mess. Hey. Either way. Alright, the next thing we learned about is optics. So we didn't actually have a textbook for that. We have a textbook for that, but that textbook wasn't good enough. So here we go. You can see it's 4A because I was in year 4 when I got this notes. Year 4, aka 10th grade. So this got some history. There's not much to talk about here other than how light travels. Light always travels in a straight line, yada yada. Light is always at the same speed, no matter what kind of light are you talking about. Okay, you can be talking about radio waves, microwaves, visible light, UV. You could be talking about friggin' alpha rays, beta rays. Nobody cares. Light always travels in the speed of 3 times 10 to the power of 8 meter per second. So or 2.97, but in the exams you can round it up to 3. And light can pass through, it can bounce off, reflection, it can disappear, be absorbed. And reflection, you need to write the normal for that. Really easy stuff. Okay. This looks difficult, but actually it's really easy as well. Basically, this is a mirror, and you look, and this is actually the object, but you're looking at the mirror. And in the mirror, you see the image of the object. So this is basically reflection, and what you see is like a straight line, but you're just looking at the mirror. So yeah, other than that, there isn't much. Okay, refraction. Refraction, basically medium 1 and medium 2. Like, if you are inside a swimming pool and you look up to the sky, you're not gonna exactly see light rays directly shining on your face. It's gonna bend a little because light do that. They're gonna bend a little when they travel into a different medium. If it's a less dense medium, then they're gonna go faster, so they're gonna bend away from normal. If it's a more dense medium, then they're gonna travel slower, so they're going to bend towards the normal. Yeah, basically that's basically it. We have refraction index, of course, and we also have total internal reflection. So if you reflect to if you emit a light ray to a different medium at a certain angle, it's going to have total internal reflection, and that angle is a critical angle, and it's different for each medium. And to calculate it, it's basically sine critical angle equals to 1 over the medium if you're emitting it from air, of course, but You know, if you're not, then it's N1 over N2, not to be confused, the incident, and then the yeah, okay, all right, okay, now it's starting to get complicated. Lens. Now there are two kinds of lens, convex lens and concave lens. So for concave lens, which are lenses that are shaped like this, there are many kinds of images that can be formed depending on how farther away from the focal length you are, well, the object is. And yeah, so here we go. This is the overview. I'm not going to talk about each one of them, but only one kind of image is formed if you're using concave lens, because only virtual image is formed, and they must be diminished as well. So this is the only kind of image that can be formed with a concave lens. So yeah, there you go. This is optics. The next chapter we're going to talk about is mechanics, and this is easily the most difficult and annoying and complicated section of the syllabus in physics ever. So this is a force and motion, or mechanics, and this book is the thickest. You know, end my life. Alright, so without overcomplicating things, I'm only going to talk about the most important points in the entire book. I'm not going to go through everything, of course. The first part of the book basically talks about distance versus displacement, velocity, acceleration. We have the whole displacement time graph. And if you, what do? You, what's the word? Differentiate it, it becomes the velocity time graph. And then you differentiate it once again, it becomes the acceleration time graph. And they're all really different. But basically, we just went over part one. If you don't know what's the difference between displacement and distance, A, you're dumb. B, point A is here, point B is here. This line is the displacement, and you can do this and go around and arrive back at point B. This is still the displacement, but this is the distance that you've gone. All right. Anyways, all right, now to the actual complicated stuff. 3 laws, Newton laws. Law number 1 is inertia. So if there is no, okay, I need to somehow go there. Okay, now inertia. If there is no net force acting on an object, it's not going to speed up. It can either not move, or it can move, but in constant speed. Now, this is kind of confusing. So, say you push an object, and then release your hand. It's still going to keep going. It's not going to speed up. It's just going to keep going. But there's no net force. If there's friction, just, working backwards, then it's going to just slow down. But there's no friction. It's just going to keep going. That's how inertia works. If you don't push it, it's just going to stay still. Law number 2, F equals to ma, the very famous, the most popular, and the most useful formula in the entirety of physics. F equals to ma. F being force in Newton, m being mass in kg, a being acceleration in meters per second square. Third law. Here we go. F equals to ma. Third law. Action and reaction. When we jump on Earth, we're actually pushing Earth a little bit away from us. But it's so little, it doesn't even friggin' matter, because Earth is so much heavier than us. it's like, I don't want to raise another example. I'm wasting time. What am I doing? W equals mg. W is weight, m is mass, and g is 9.81. Acceleration due to gravity. It's constant. If you're on Earth, it has to be 9.81. Okay. So say right now I'm 55 kg. So let's see what's my mass. 55 or 9.81. 539.22 newtons. So, there you go. And right now I'm on the 32nd floor, but I don't think I'm high enough to actually make a difference or anything. Alright, so your weight is the same, but your mass is different. Well, at least the way it's detected is different if you're on a lift / elevator. Yep. Alright. I'm just gonna skip a bunch of these. Alright, now this is really tough. This is really tough. Moment of a force equals the force times the perpendicular distance from that point. Like a door hinge. So look at this table and you know what I'm talking about. Like a door hinge, and the direction of the force applied to such a point in relation to its pivot is really important. But this is still one of the more easier parts in the whole thing. It's really important to know which point is the pivot, and it's also important to know the weight of the entire thing. So say this one. But yeah, other than that, that's pretty much moment. Now, this is even more complicated. This is work done and energy transfer. So now we're talking about energy. Say you push this box from here to here. There is no work done in that case, because no work is done if you're lifting a box and walking forward. There's no work done on the box because it's perpendicular. It's 90 degrees. It means nothing. But say if you drop an eraser, I got it. It would have been very embarrassing if I didn't catch it. Then this thing gained kinetic energy but lost potential energy. And at the same time, there is work done against air resistance, but of course you need to ignore it because air resistance is annoying. But there you go, work done. And kinetic energy is 1/2 mv squared, v being velocity, and potential energy is mgh, mass, times 9.81 times height, right here. Now this can get very, very, very complicated, especially when it comes to, ball sacks swinging from pendulums. I hate those friggin' questions. Ball sacks. But yeah, we get a bunch of pendulum questions, which I hate. These are the friggin' pendulum questions, and it's not fun when there are two objects being swung around, not one. But you get the idea. Power equals to energy over time. So power times time is energy. All right. Up next we have, see, it gets really stupidly complicated when there's a friggin' roller coaster. Yeah. And you also need to calculate the work done against friction. Okay, anyways. Momentum. Everybody loves momentum. So for momentum, momentum, P equals to m times v, mass times velocity. So two objects, okay? One is moving, one is not. Boom, now they're both moving. This is called the elastic collision. Yeah, Nope, wrong. If they stick together, it's inelastic. If they collide and then they both move on, but one of them speeds up, it's elastic. If they collide, but boom, explosion. There's that. Okay. At the bottom of the page, yeah, pretty much it. So, say a car is moving and suddenly a giant piece of rock smashes it, but the car keeps on moving, then it's gonna slow down. Alright, I feel like I should also mention the change in momentum. Yeah, you know what's up. You know what's up. Now we have all sorts of questions about how, say, you shoot a pumpkin and how the bullet slows down after it passes through the pumpkin. Those questions are really, really annoying. But other than that, we will move on to an even more annoying part of the book, and that is one and only projectile motion. Alright, now this is very, very, very annoying. Now, this is very, very, very annoying. One of the worst chapters in physics, in my opinion. Because, say, this is the object, right? You launch it, boom, you launch it, and it goes like this, and it lands back. You need to break it down to two components, the horizontal component and the vertical component. And there's a huge misconception that I've made, and I shouldn't have, and that is when it travels horizontally, like for the horizontal component, say it travels like this, but you look at it on a bird's eye view, so it's like this. It doesn't speed up, it's constant always, but if you look at it in another perspective, so it's a vertical component, it actually speeds up, and then it has no speed, and then it speeds up again as it goes down. No, actually, it doesn't speed up when it goes up. It actually speeds down. It actually decelerates using the equation 9.81. And I forgot to mention this, but earlier on in the book, we have the four very importante equations. That is okay. Shoot. These formulas, v being final velocity, u being initial velocity, a being acceleration, time being t being time, s equals to displacement, so v equals to u plus at, s equals to 1/2 bracket u plus v times t, s equals to ut plus 0.5 at squared, and v squared equals to u squared plus 2as. Now these are really important, and they are incredibly useful when calculating the projectile motion, because you want to know how much time is required for an object to go up this far and then go back down and then touch the same spot. And with that time, you can also calculate how far that object had gone, because you kind of already know its velocity, right? But you also need to be careful of the angle of the thing. Yeah, other than that, projectile motion. Now, in my opinion, what's an even worse chapter is, of course, circular motion. Circular motion, it's really annoying. I didn't study calculus, I didn't take calculus, so the whole radian thing is already throwing me off. But basically, 1 radian equals to 180 degrees over pi. So, if you want to go a full circle, okay, this is the center, an object goes full circle, it's 2 pi. Basically 2 pi over time equals to v. See, this is already confusing. 2 pi over t equals to angular displacement per unit time. So it's angular speed. And then we have the linear speed, because when it moves around, it doesn't just move around. It has a centripetal force going from here to the center, and then we have another tangent where it goes up, and it's actually its linear speed. And its linear speed is basically r times the angular speed, r being the radius. It's already really confusing. And then, of course, we have acceleration, of course. And then F equals to mv squared over r is the centripetal force. But it's not that simple, of course. Again, in the event of this thing, circular pendulum. You need to break it down. We have the vertical component, and then we have the horizontal component, and how, and of course the cosine theta, the sine theta. You know the drill. And we have the whole skidding thing. Because sometimes say this is the slope, and the car is going this way. And sometimes the friction goes up, sometimes the friction goes down, and depending on how fast the car going and how strong is the centripetal force. I guess the most abstract part of the book is gravitation, because first of all, we have F equals to G m1 m2 over r squared. But of course, we also have other equations, like G equals to big G, big M, and big G is like I think big G is a constant over r squared. So that is the gravitational force in relation to how far you are from the surface of that planet. And then we have the gravitational field strength equals to gravitational force over mass. And yeah, it's really complicated. And then we have the whole orbit thing, which I'm not that clear conceptually still, where the gravity is actually kind of related to how fast a satellite orbits, but go figure that out yourself. I'm a terrible teacher. Isn't there supposed to be a page that explains this? Okay, there we go. Oh my goodness, there are two kinds of acceleration. One is passive, one is active. And big G, big M, small m over r squared equals to mv squared over r equals to mr omega squared, omega being angular speed. Waves. Alright. 12 years ago, someone spilled chocolate milkshake on my waves book. I just remembered that. Alright, so waves is way easier, but you can still fuck it up if you're not careful enough. Two kinds of waves. The converse wave, the transverse waves, and the longitudinal waves. Transverse waves are basically electromagnetic waves, aka light waves, and longitudinal waves are basically mechanical waves, aka like sound waves and such. So for longitudinal waves, they have crests and troughs, ups and downs. And for longitudinal waves, we have rarefactions, the farthest part, and the compressions. Now we have multiple units for waves. We have amplitudes, period, frequency, wave speed. V equals to f lambda, f being frequency. Frequency is how many full periods, well, actually, how many wavelengths can you have in 1 second? So say in 1 second you do this. This is one wavelength. You go from an original point back to the original point, with a crest, with a crest and a trough. This is one wavelength, and V equals to F lambda. Lambda is a wavelength, and 1 over F is period. So how long does it take to go for one full wavelength? And V being the wave speed. Yep, that's all you need to know for the first part of the book. Alright, the second part is what we call waves. Okay, so we have these, right? Now it's gonna get complicated when you suddenly decide that the okay, I'm just gonna skip a few parts. When you suddenly make the medium shallower or deeper, the waves are going to change. Now the frequency is never going to change, but from deeper region to shallower region, the wave speed decreases and the wavelength also decreases. And then we have diffraction. So you can see right here very clearly. This is how diffraction works. It passes through a slit and it just changes direction. And the degree of spread of diffraction is actually different depending on the width of the slit and the wavelength of the wave. And of course we have interference. I love interference. Alright, so when there are two waves and they meet each other, if a crest and another crest meet, they're going to become a big crest. If a trough and another trough meet, they're going to become a big trough. And these two types of interference are also constructive interference. But for destructive, if a crest and a trough meet, they're going to become flat. That is destructive. And you can actually see antinodal and nodal lines, where in antinodal lines, it's all constructive interference, and for nodal lines, it's all destructive interference. And you can actually calculate that stuff. I mean, there's a way to calculate this stuff, I think. But I can't find it in here for some reason. Okay, anyways, stationary waves. I think if the tension of the string is stronger, then the number of loops are smaller, I guess. Where is the slit? Where is the slit equation? There we go. There we go. There we go. Finally. Delta y equals lambda d over a. So y is the distance between each fringe. All right. So delta y equals to the separation between each fringe, or each antinodal line or nodal line, and a being the separation between each slit, the two slits, and d being the distance between the point of emission and the point of reception, and lambda is the wavelength. There is another equation, by the way. There's another formula if you want to know which order of the fringes are, because you know, you get the central order, and then we got the first minima, first maxima, second minima, second maxima, you know, light, dark, light, dark, light, dark. There's another equation, n being the number of orders, d sine theta equals to n lambda, and these two formulas are incredibly important, and I'm just gonna leave it at that. I'll take a rest now. There's also a way to turn a longitudinal wave into a transverse wave graph by measuring how far is its original point and say a point. of that particle and the total displacement traveled by that particle, and you could just map it out. It can be negative, it can be positive, so it becomes a sine graph of sorts, and that's how you do it. And if it does this, it's a compression. If it does this, it's a rarefaction. And the highest point actually has and the lowest points actually have the highest displacements and the lowest displacements. All right, I have taken a break. Now I'm back. Electricity and Magnetism, Book 4. Where is it going to end? When is it going to end? We have no idea. And physics is the easier one out of the three. I mean, the biology and chemistry, this is actually easier. Alright, so again, I will not go through every single detail in this book. I will skip the easier parts. I'll skip a few of them because I am not going to assume that you guys are stupid, okay? I'm just kidding. So, okay. Starting off, we have the one and only electrostatics. Now, what's up is you need to notice two things. Positively charged and the negatively charged. Protons are positively charged. Electrons are negatively charged. And they attract with one another. But say two protons, they do not attract one another. In fact, they repel against one another. And that is why in the nucleus of an atom, a bunch of protons are stuck together. This is quite a miracle. I don't know how. Are they doing it? What the hell? All right. Now we have another concept called earthing. Right now I'm standing on an object. That is the floor of this apartment that is connected to the ground in the outside world right now. So I'm Earth. I'm neither positively charged or negatively charged because I am one with Earth, and Earth is always neutral. So now say you have some balls, some metallic balls here. Say it is originally negatively charged, and then you touch it and you're standing on the ground. Then you earthed it, and now it's neutral again. It has both positive and negative charges once again. Earthing. Here you go. Then we have the electric field. The field goes from the positive to the negative. Right here. The field is strongest in the nearer points, in the points nearer to the particle. So that's pretty much all you need to know. Now, the second big concept that you need to know is the difference between series and parallel. This and this. These two are electric appliances, and they spend energy. If they are connected in series, and say the electrical source is right here, so these two things will spend all the voltage. But, okay, let's say each one of these will spend 3 volts. So let's say the EMS of the thing, the battery, provides 6 volts. Then each one of these appliances are going to receive 3 volts, because 3 plus 3 equals 6. But if you connect them to parallelly, then each one of them is going to receive 6. And even though this thing releases 6, it releases twice its speed. aka twice its current. So both of them are equally as lit, equally as receiving. That is why the electrical appliances in our apartments and in our houses are all connected in parallel. Otherwise, if we turn on a bunch of lights, then all of the lights are going to be super dim. But if we only turn on one, that light is going to be super bright, which is kind of dumb. Okay, now we have some more formulas. The electrical field strength equals to F over Q. F being force and Q being charge. And we have an incredibly important formula that is E equals to Q over 4 pi E naught R squared. E naught is not my name. Okay, here. So this is the electrical field charge around a point charge. Electrical field strength around the point charge. And this is very important. We also have E equals to V over D between parallel charged plates. So D being distance, V being the potential difference or voltage. Alright, that is basically chapter 1. Now we move over to chapter 2. So we have voltmeters and ammeters. And voltmeters, okay, if I haven't mentioned the units, volt is basically joule per charge, the number of joules per charge, aka the number of energy, the amount of energy in each charge. That is volt, and that is also potential difference. And you can actually measure the potential difference in a section of a circuit using the voltmeter. Or you can actually, and you can measure the current of a section of a circuit with an ammeter. And current is basically charge per second. So it's like how fast is charge, or more like how fast are the electrons moving in the circuit. So, charge per second. So voltage is like how much is in a car, and how many people are in the car. And current is like how fast is the car. That is why power equals to VI, power being watt and watt being joule per second. And we also have R. R is resistance in the unit of ohm. V equals to IR, that is Ohm's law. And V being voltage, I being current, R being resistance. So yeah, there's that. There is that. There are many different ways of connecting a circuit. But here you go. Electrical appliances. You need to have an electrical appliance or a resistor in your circuit. Otherwise, it'll become a short circuit. Everything's gonna burn. You're gonna be dumb. You don't want to do that. All right. The next thing you need to learn is resistivity. R equals to PL over A. Right here. Now, resistivity is different for each resistor. And, nope, I am wrong. Duh. Resistance is different for each kind of resistor. And then we have resistivity, and it's constant, but it's different for each material, but it's always the same. Say, copper. The resistivity of copper is always the same regardless of its length, because in the full equation, PL over A, L being length and A being the surface area. And say the wire is uniformly cylindrical. So you can find the surface area by, radius squared times pi. So the larger the surface area of the wire, cross-sectional surface area, the smaller is the resistance because there's more space. But if the wire is longer, then it takes more time. So R equals PL over A. Okie dokie. It's going to get more and more abstract here. Okay, so if two resistors, say this is 2 ohms, and this is 2 ohms. If they're connected together, then okay, this is better. Then overall we have 4 ohms, 2 plus 2. But if it's connected in parallel, it's 1 ohm. 2 ohms, but 1 over 2 plus 1 over 2, and then the whole thing, the reciprocal of the whole thing is 1. So there's that. There's how you calculate the resistance if it is connected in the parallel. Right here. All right. Of course, short circuit. You can't do that. It's stupid. Why would you want to short circuit it? Okay. Ideally, a voltmeter has infinite resistance because you don't want any current to pass through the voltmeter. Otherwise, it's pretty much pointless because the voltmeter needs to, detect the potential difference of a section of a circuit, not its own potential difference, but the circuit, that section's potential difference. And ideally, an ammeter should have 0 resistance, so current can just pass through it easily. But there we go. There is that. Moving over, we have chapter 3, and that is domestic electricity. And for domestic electricity, we have power and we have rated power. So it's a little confusing. Okay, so power equals to VI, P equals to VI, but it also equals to I square R, also equals to V square over R. So there's that. Now, there's rated power. Every electrical appliance has a rated power, which is like something watt and then something volt. So with that, what is its current, and what kind of fuse you want to install in beside those electrical appliances. Because if there's too much current passing through it, then it's dangerous. So if the fuse blows, the circuit cuts off and there's no electrical current passing through it. So hey, everyone's safe and sound. But anyways, back to rated power. Power rating, it's supposed to be the power to supply it, it's, you don't need to power, say a flashlight. A flashlight is 1.5 watt, 4.5 volt. And in that case, then you can power it 1.5 watt. It's fine. You can also power it even higher. It's also fine. But this is basically the rated power. So it has to be this way. I guess that's how I would explain it. All right, we have okay, if you don't know what's the difference between AC and DC, AC only has one direction. AC basically vibrates, like the current goes this way and suddenly it's going to go that way and suddenly it's going to go this way again, which is a little annoying. DC only has one direction, the boy band. Anyways, we have the electrical socket. The 3-pin plug-in socket. It's actually different in each country, but in Hong Kong it's a ELN, my initials. So it's ELN, Earth, Live, Neutral. And this is how electrical appliances are connected. So we have the live wire, which is the wire that carries the current. We have the neutral wire, which carries the current away from the electrical appliance. And then we have the earth wire. In case something happens, it's going to switch to the earth wire and it's going to earth the whole thing and not make it super negatively charged so that it doesn't blow up or anything, which is really smart. I think American sockets only have 2 pins, so they don't have earth wires. Dangerous. Anyways, household wiring. Gosh darn it. everything's falling apart. We got the main rings, we got the main sockets, and we got cables everywhere. We got a consumer unit, we got a lighting unit, we got different units, and then we got the kilowatt hour meter, which calculates the, you know, how much electricity, how much power is used. Now for magnetism. So this is the Earth's magnetic field. The North Pole of the Earth is actually not north, it's actually south. That is why in our compasses, the north points to the North Pole, because it's actually south, and north is attracted to south. It goes from north to south. So North Pole is a lie, it's actually South Pole. We have been bamboozled. Yeah, there's that. So it goes from north to south. That is the first thing you need to know, and now it gets complicated. So first of all, this one. Current carrying wire. Okay, so this is the wire, and if the current goes from here to here, then it's like this. My thumb points to the direction of the current, and my fingers basically imitate the magnetic field generated because of the current. So now it's like this. And this is the opposite side. You get the idea. And then we have the solenoid. Say this is the solenoid, and it's basically coils that go like this, so the currents are going like this. So if the solenoid goes this direction, my fingers are imitating the solenoid, then the current is going to go this way. So, you know. And yeah. Basically there's that. And of course there is a formula surrounding it. We have B equals to mu naught I over 2 pi r. And we also have for the solenoid, we have B equals to mu naught big N big I over L. Of course, mu naught is a constant, and it is the permeability of free space, and the constant is 4 times pi times 10 to the power of -7 Tesla meter per ampere. Ampere is, you know, unit of current. I is current, 2 pi r, r is radius. Same goes for solenoid, the big N being the number of turns, and L being length, and in unit length. So yeah, there's that. I guess there's a bunch of other stuff that I should probably spend some time in, some application stuff, but nothing all that important. It just, you know, says how earphones work, how magnetic levitation works, you know, stuff like that. Now, this is classic. Alright. So here we see a current, and right here we have a magnet with a north pole and a south pole. And what's going to happen is that the wire will experience magnetic force. This FBI. F is the force, B is the magnetic field direction, and I being the current. So say the current goes from you to me. That's the current. And this is north and this is south. Then the wire will go up. It's going to go up because this is pointing upwards. So this is how it works. But this only applies if you're inducing a magnetic force. If you already have a magnetic force and you already have a current, but you're trying to induce that. If you have a magnetic force and you already have a magnetic field and you're trying to induce a current, you use this hand. It's kind of different. Hey, there we go. So similarly, if the magnetic field is not exactly perpendicular, you can still calculate it with this formula, which is actually F equals to BIL sine theta. B being magnetic field strength in the unit of Tesla, and we also have F equals BQV sine theta if you're talking about magnetic field acting on a charge, particle, and inducing magnetic force. Yeah, it's starting to get complicated. So this is basically how motors work. So you have a coil, it's a loop, and then you have a magnetic field, and then you have the current. So one side goes up and one side goes down, and it just constantly spins, and this is how motor works, which is pretty smart. Gosh darn, pretty smart. As you can see, and motors have different components as well. Carbon brushes, a split ring. If it's not a split ring, then you're gonna have a short circuit because the wire can just because the current can just go through the split ring, go through the ring, and skip the whole coil part, which is dumb. Anyways, yeah, there's not much to talk about. I guess I can show you this. All right. Again, moving charges. So, say if, all right, this is getting really complicated. Say if the magnetic field goes from me to you. So north, south. And we have a positively charged particle. So positive to negative, so it's like this. Now FB, me to you, I, so positively charged particle here, but then we have the magnetic force. So if it's launched like this, it's going to spin back up like this. If it's negative, it's another story. So it's going to go the other way. Nope, it's actually going to go the same, because if a negative particle is released here, it's still going to go up. But if it's released here, it has to go down. But yeah, there's that. There is that. I still haven't mentioned Lenz Law. Okay, so Lenz Law. What the heck is a Lenz Law? Okay, there we go. A classic. 'Tis a classic. So you have a current, and it's going like this. Okay, so say the current is now this is a little abstract, but say if you have a current, and this is the current. Well, nope, there is no current at first. There's a coil. So there's a bunch of wires, but nothing's going on inside them. No electrons are moving. There's a wire, and it's like this. All right, just going like this. And then a magnet. North this side, south this side. A magnet, north, south. It's about to go into the thing. Now, what the thing is going to do is that it's going to try to oppose that magnet by making this side south and this side north, which means the current is going to be because this, so this side south, this side north, so now the current is going to go this way. But if the magnet is leaving this side north, this side south, If it's leaving, it's going to try to attract the magnet again. So north, south, north, south. So north this side, south this side. So the current, north this side, south this side. So the current goes this way. And that is basically Lenz law. It tries to oppose the change causing it. I'm really tired right now. We also have magnetic flux, which is sort of out of the syllabus, but you guys should check out as well. And we also have transformers. One more thing before I close this book. Transformers. Oh, one more thing. One more thing. Sinusoidal. I don't know. But this thing. Say this thing is a sinusoidal. So say there's an AC current, and it and the current is going like this, and then this, and then this, and then this, and then this, you know, yada 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 yada. Now you get the highest possible voltage given, and you divide it by the square root of 2, then you get the average. So this is basically what's happening here. RMS, same thing. What you do is you get the mean value of I square, and the mean value of I square is basically the current squared times the period of that current, and it's so hard to explain this, so I'm just gonna show you this right here, and you can basically calculate the RMS value, and I don't know where is transformers, but I could have sworn there is a part in this book that talks about transformers. Transformers, where is it? I can't find it. Okay, so I'm gonna use my own notebook, which is a mess, but transformers right here. As you can see, it's basically two magnets, 2 sets of coils, and by supplying the first coil, the primary coil, with current, you can actually generate current in the second coil as well, but because they're not connected, so the current is not the same, and the primary coil current and the number of coil turns, the ratio, is actually inversely proportional, but the voltage is directly proportional. So say with 2 magnets here, 30 turns and 60 turns, and in 30 turns we supply 12 volts, and in 60 turns we're going to get 24 volts. But for 30 turns you supply, say, 10 ampere, then right here, 60 turns, you're going to get 5 ampere. So that's basically what's going on. The last book, okay, the last book to discuss is book 5, Radioactivity and Nuclear Energy. I'm dying. So, this is the electromagnetic wave spectrum. We have the visible light right here, And anything more than that is UV, X-ray, and then, you know, radiation, like alpha ray, gamma rays, beta rays. And alpha beta rays are nuclear radiation, so is gamma rays. Now, there's a difference between alpha, beta, and gamma. Alpha rays are basically helium nuclei, and beta rays are basically fast-moving electrons, and gamma rays are basically electromagnetic waves of very high frequency. So the most tangible one is this one, alpha radiation, and it also has the strongest ionizing power, so this thing is actually the deadliest, even though gamma ray penetrates anything almost, and it's also super duper deadly. Yep, the ionizing power is different. And there's a way to detect it with a diffusion cloud chamber. So we have the cloud chamber tracks. Basically these 3 tracks, and they're different for each type of nuclear radiation. And you can also use the Geiger-Muller counter, the GM counter, the very iconic crackling sounds in Chernobyl, basically the GM counter. Again, the penetrating power and the range is all pretty different. And there is that. And it also reacts differently with a magnetic field, because one of them is positively charged. That is the helium nuclei. Alpha radiation is positively charged. Beta radiation is negatively charged because it is an electron, and gamma radiation it has no charge. And yeah, that's basically it. Now, up next, we are going to talk about the okay, so atomic structure, everybody knows that shit. Radioactive decay. So a radioactive element can decay. They can suddenly decide to release a helium nuclei for some reason. So they're going to decay. Sometimes they're going to decide to release an electron for no good reason. So this is how they decay. And you can actually, there's a half-life. Now, they decay randomly. You don't know how they decay, but they actually have a half-life. So there's a graph, and with this data, you can actually tell how old is a radioactive element by checking on its radioactivity with the equation A equals to Kn, and K being the decay constant, but I prefer A equals to 1 over 2 to the power of n, and n being time over number of half-lives. So we know how many half-lives have that radioactive element gone through. There's also another equation here. A equals to A naught times E, E being the opposite of a natural log, to the power of negative K times T, T being time, and A naught being the initial activity, of course. And other than that, I think this is it. I think this is it for yeah. Yeah. Oh, we also have nuclear fusion and nuclear fission, of course. Finally, we have the ultimate formula of all times: E equals to mc squared. And it applies to both nuclear fusion and fission. This is nuclear fusion, very obviously, where two nucleus fuse to form one bigger nucleus and one neutron. Or we have fission, where one giant nucleus break apart and then release more neutrons as well. And we have E equals to mc squared, or delta E equals to delta mc squared. E being the energy released, measured in joule. Delta M is the loss in mass, measured in kg. And C is the speed of light. It's always constant, about 3 times 10 to the power of 8. And you need to square it. And usually, we have the U value. Usually for the mass, it's not like we're going to calculate the exact weight of a friggin' particle, okay? We do it in the unit of U. U being 1 over 2 times 1 over 12 times mass of a carbon-12 atom, which is about 1.661 times 10 to the power of negative 27 kg. And with that, 1U equals to 1.661 times 10 to the power of negative 27 kg equals to 931 mega electron volt. Yeah, other than that, we have finished it. Thanks for watching. I need to take a rest. I'm a broken man now. Yeah.